Looking at example 6 on the solving trig equations notes. This time we don't have different trig functions. We have the same trig function sine here as we do here. And we have the same argument x here and here. The thing that's different is the fact that the first one is being squared and the second one is not. So we can't combine them. They're not like terms. But remember that sine squared of x is the same thing as sine of x times a second sine of x. We could always write it like this with the parentheses, but we get tired of the parentheses, so we just use this shorthand. But this is the same thing, and we should think about it like this. So again, thinking about this purely algebraically, we've got stuff squared. I'll call that stuff a. So this is 3 times a squared minus 5 times, it's the same stuff as before, right? This sine of x is the same stuff that we have right here, it's just not being squared. So we have minus 5a minus 2 equals 0. So I'm actually going to leave, that substitution in this problem. You don't have to do it this way, you can skip the substitution. But I think it's helpful for a lot of people to kind of separate the algebra from the trig. So let's let the sine of x equal a, and then I'm going to replace every sine of x that I see with an a, and I'm going to turn this into an old school algebra problem. Okay, and when we try to factor this, we've got some choices. One choice is try to factor, another choice is use the Pythagorean theorem. No, the quadratic formula. Some people like the quadratic formula because there's no guessing and no trial and error. It's just a formula to plug and to chug. But I would recommend trying the factoring. More times than not, these problems are going to factor. It's not guaranteed, of course, but factoring can be very quick, especially when we have small primes like 3 and negative 2. There's really not a whole lot of ways that we can break up 3 and negative 2. The only way we can get 3a squared for our first term is if we put a 3a and a 1a in our two factors. And then we've got two choices here, right? We can either put the 1 here and the 2 here, or we could put the 2 here and the 1 here. And we can deal with the pluses and minuses later. Right now I just want to focus on those two choices. Now if we put the 1 here and the 2 here, then when we distribute this out, we're going to get 3 times 2 to get 5, well 3a times 2 to get 5a, and 1 times a to get 1a. Did I say 3 times 2 is 5? 3 times 2 is 6. 3a times 2 is 6a, and then 1 times a is 1a. And then 6a minus 1a can give us the 5a that we're looking for. So that sounds pretty promising. Now if we try to do the 2 here and the 1 here, then think about what we would get. We'd get a 3a times 1 and a 2a. And that combines by adding to get 5. So that's actually kind of a problem. We can get 5 either way. So now we have to consider the signs. Since we have to get a negative 2 here, we know that these have to be opposite signs, right? So if I put a minus here and a plus here, then that's going to give us a negative 2 when we multiply negative 1 times positive 2. So that's important. We know that these two numbers that we put here, whether it's a 1 and a 2 or a 2 and a 1, they have to be opposite signs, which means when we distribute, we're going to get a positive, in this case 6a, and a negative, in this case 1a. 6a minus 1a is going to give us positive 5a. Well, that's a problem because we want a negative 5a, but that's not to worry. We can change the negative 1 to a positive 1, and we can change the positive 2 to a negative 2, and all is good with the world. Okay, so this is the only way that we can factor it. There are other methods, and it's fine if you want to use a different method, but this is a way to do it. Anyway, we've factored it, and we've got this all-important equals 0. Remember, we don't really care about factoring if we don't have 0 on the right side of the equation, because when we have something times something else equal to 0, that means that either the first thing or the second thing has to equal 0. So we can get a equals negative 1/3, or we can get a equals 2. Now if we started with this equation and we asked solve for a, then we'd be done. We'd have two answers. And we're not surprised to get two answers. The fundamental theorem of algebra tells us that a quadratic is going to give us two solutions, and those are them, right? Negative 1/3 and 2 are the solutions. But our original problem isn't solve for a. Our original problem is solve for x. And x is embedded into something more complicated. X is embedded into this sine of x equals a. So I'm going to convert back now to our land of x's and realize that if a equals negative 1/3, then sine of x is equal to negative 1/3. And if a equals 2, then sine of x is equal to 2. So those are the two equations that I need to solve. So when we think about this one, we say, okay, well, we're looking for an angle who, when we take the sine of it, we get negative 1/3. So we can take the arc sine and find that we get the arc sine of negative 1/3. Just like we saw on a previous problem, not the last one, but earlier on, I think it might have been example 3. Or maybe it was example 4. What was it? Yeah, it was example 4 when we had the inverse cosine of 1/5. Right? That 1/5 was not something we recognized from the unit circle. This negative 1/3 is not something that we recognize from the unit circle. So I would leave the exact answer looking like this. Okay? Plus 2 pi n, of course, because we're looking for all the solutions. And then this is an odd function whose period is 2 pi. So thinking back to our ambiguous case, remember when we found an angle with the arc sine, we would also consider pi minus the angle. Pi minus the angle is going to also give us the same sine value. Pi minus theta is a reflection of theta on the y-axis. I'll say that again. Pi minus theta, if this is theta, then this is pi minus theta. They're a reflection on the y-axis, and they have the same sine value because they are level horizontally. So that's the thing we have to keep in mind when we're taking arc sine. Remember, it's a different rule for each of the three trig functions. Cosine, we do plus or minus. For sine, we do the regular one and then pi minus the regular one. And then for tangent, we just get the one answer, but instead of plus 2 pi n, we just add 1 pi n. So anyway, that is the set of solutions we get from this first equation. Now, before you just jump blindly into doing the same thing with the 2 that we did with the negative 1/3, let's think about how 2 is greater than 1. And the sine of x is never greater than 1. This is not possible. There's no solution from this equation. Sine of x never equals 2. So forget about it. It doesn't give us any new solutions. So these would be all the solutions to the original equation in exact form. If we were interested in just finding that finite list of values that are between 0 and 2 pi, well, we do the same thing we always do. We generate the lists and we find all the different values that are between 0 and 2 pi. So we can use a calculator for this. That's okay. So let me pull out my calculator. Boom! And as if by magic, Desmos is right here. So what is the inverse sine of negative 1/3, or the arc sine of negative 1/3? It's a decimal value. It's approximately negative 0.340, I guess. Approximately negative 0.339, but that 8 makes the 39 round up to a 40. And then if we look at pi minus that answer, I'll just call this, I don't know, I'll call this A, and then I'll do pi minus A. And then this is going to give us the answer 3.481. That one doesn't change because of the rounding. Okay, so are either of these answers between 0 and 2 pi? Well, 0 is between positives and negatives, so clearly this is no good. But if we add 2 pi to it, we should get something between 0 and 2 pi. So I'm going to take a plus 2 pi. That's letting n equal 1 here, and that's going to give us 5.943. 5 5.943. Or in exact mode, that would be the inverse sine of negative 1/3 plus 2 pi. Okay, so that's the exact form. The 5.943 is the approximate value. And then the other one, 3.481, that one's all good. That one is between 0 and 6.28, so we're happy with that. How do I know there's not another one? Because if I add 2 pi, I'm going to be outside of the interval 0 to 2 pi. So where did that one come from? That one came from pi minus the inverse sine of negative 1/3. Again, both of these are the same. It's just that one of them is exact and the other one is rounded. And again, we can double check these in a calculator by going back to the original equation. So since I have Desmos open, why not? Let's give it a try. We've got 3 times the sine squared of x minus 5 times sine of x minus 2. And this isn't something I would expect you to graph by hand, but it's very easy to graph this in a calculator. And if we go from 0 to 2 pi, which is going to be somewhere around here, a little bit past 6, we see that we do have two solutions. They are 3.481 and 5.943. And lo and behold, those are exactly the two answers that we got right here. And you can see that we do have answers spaced out every 2 pi as well. So this one is 2 pi less than the 5.943. And then this one over here is going to be 2 pi more than the 3.481. And that's represented in all the solutions that we have right here.